Schedulers decide who runs next, and the Pattern Mastery 100 Essential Task Scheduler tests if you can translate a real-world CPU cooldown rule into tight math. Interviewers love it because brute force simulations get messy, but an elegant counting plus formula nails it in one line. Let's master it with BASIC and ship an optimal solution in minutes. Let's break this down. We're given a list of tasks labeled by letters, for example, A, Z, and a cooldown N. Between two runs of the same task, there must be at least N idle intervals. We must compute the minimum number of intervals, tasks plus idles, to finish all tasks. Now let's assess it. A priority queue simulation works but is overkill. There's a clean formula. Let max be the maximum frequency among tasks, and num_max be how many tasks achieve that frequency. We build max 1 full frames, each of length n+1, task plus cooldown slots. The final layer places the num_max most frequent tasks. The answer is max len tasks, max, 1, n+1, plus num_max, because if we have enough other tasks to fill idles, total time is just len tasks. Here is the structure. Plan, count task frequencies, compute fmax and num_max, then apply the formula and return the max with len tasks. Handle edge cases like tasks equals. Now let's implement the greedy heap-based simulation, repeatedly selecting the most frequent tasks while respecting cooldown rules. This approach simulates time, always choosing the most frequent available task, while tracking cooldown periods. Step 1. Count task frequencies. We begin with a frequency map to count how many times each task appears. This will help decide which task to schedule next. We loop through all tasks and increment their counts. This gives us a complete frequency table. Step 2. Build max heap of task counts. We create a max heap so we can always pick the task type that still occurs the most. This ensures tasks with heavier demand are handled early to reduce idle time. We push each task count into the heap so the largest counts rise to the top. Step 3. Cooldown list. We keep a list of tasks that are cooling down. Each entry stores when the task is allowed to run again and how many executions remain. Step 4. Simulate the timeline. We start a clock that advances step by step, like a real schedule. We continue simulating as long as we still have tasks to schedule or tasks waiting in cooldown. Attempt to execute a task. Each loop iteration represents 1 unit of time passing. If the heap isn't empty, we take the most frequent remaining task, execute it once, and decrease its count. If the task still has occurrences left, we put it into cooldown, setting the time when it becomes available again. Check if a task finished cooling. We check whether the earliest cooling task is now ready to be used again. If ready, we remove it from cooldown and push its remaining count back into the max heap so it can be scheduled again. Return the final time. When both heap and cooldown list are empty, every task has been executed. The current time value represents the minimum total time required. And that's how this algorithm works. It first picks the most frequent executable task, then manages cooldown periods while simulating time until all tasks are done. Efficient, simple, and elegant. Let's test our scheduler with these tasks. Because the same letter needs a cooldown of 2 units, we must space out repeated A's and B's. The most frequent tasks are A and B, 3 each. To respect the cooldown, they must alternate with idle spots when needed. A valid timeline is 8 units long. For example, A, B, idle, A, B, idle, A, B. And that's exactly what our program outputs, 8, matching the expected result. So, our implementation is correct. The scheduler handles cooldowns properly and computes the minimal timeline. Now let's implement the counting-based formula, using task frequencies to compute the minimum intervals needed without simulating the entire timeline. This approach does not simulate time. Instead, it uses a mathematical formula to compute how many idle slots are required. Step 1. Count task frequencies. We begin with a frequency map to count how many times each task appears. We loop through the tasks and update their counts, building a full frequency table. Step 2. Find the maximum frequency. We prepare a variable to track the highest frequency among all tasks. We scan every task type and keep the maximum count. This tells us which task type drives the scheduling constraints. Step 3. Count how many tasks have that maximum frequency. We also need to know how many tasks tie for that maximum frequency. If multiple tasks share the same highest frequency, they influence how we structure the idle slots. Step 4. Compute idle slot structure. We imagine arranging the most frequent tasks first. Between them, we form max_freq, 1 partitions, gaps. Each partition has room for other tasks, but if multiple tasks tie at max frequency, they help fill the gaps automatically. We compute how many empty spaces remain after placing all high-frequency tasks. These are potential idle slots. We then compute how many non-max frequency tasks are left that can fill those empty slots. Finally, if those tasks cannot fully fill the gaps, the leftover space becomes actual idle time. Step 5. Compute final answer. The total time is simply #tasks executed plus #idle slots required. That gives us the minimum possible interval count. And that's how this algorithm works. It first analyzes frequencies to calculate unavoidable gaps, then uses a formula to compute exactly how many idle slots must be inserted. Efficient, simple, and elegant. Let's test our scheduler using this task list. A cooldown of 1 means each repeated task needs at least one different task between runs. The most frequent tasks are A and B, each 2 times. Using the scheduling formula, we see that all tasks can fit without any idle time. So the minimum schedule length is simply the total number of tasks, 6. And that's exactly what the program outputs, matching the expected result. So, our implementation is correct. The math-based approach efficiently computes the minimal valid schedule. Schedulers decide who runs next, and Task Scheduler turns that real-world CPU rule into math you can master in minutes. It's a brilliant test of logic, counting, and optimization. Let's do a recap. We're given tasks and a cooldown value n, meaning identical tasks must have at least n intervals between them. The goal is to find the minimum total intervals, tasks plus any necessary idle time. While simulating with a priority queue works, it's not efficient. The elegant way is counting. Find the most frequent task, fmax, and how many tasks tie for that frequency, num_max. Use a formula that accounts for full frames of cooldowns and then fills remaining slots. The plan. Count frequencies of all tasks. Compute fmax and num_max. Apply the formula, max total tasks, max, 1, n plus 1, plus num_max. This gives the minimum time with no unnecessary simulation. We executed this logic cleanly, counted frequencies, applied the formula, and ran the code successfully on LeetCode without any errors. All test cases passed. The math perfectly matched the scheduling outcomes. The big takeaway, math beats simulation. Once you spot patterns in frequency and gaps, scheduling problems become pure arithmetic.